So hi there. We're going to take a look at the last property. This one's a little bit more out there. We're going to talk about this notion of well-defined. So this is a little bit more kind of trickier and abstract. So definitely ask questions if you have them. So well-defined. So what we're asking here is let's let n be a natural number. And for any a and b that are in z sub n, we're going to propose to define an operation of a bar raised to the b bar by setting a bar to the b bar and rewrite it as raising a to the b power and then taking the bar of that, or finding the congruent value of that, whatever mod we happen to be working in. Okay. The reason we're thinking about this is because of the fact that we've got these two other operations, which were proven earlier. It's something we've actually been talking about since the beginning of chapter 7. This notion that I can add two modules together. And really what this means is this is like any number, any equivalent number in a modulus, and I add that to some other number over here. And that's actually the same thing as adding the two actual integers and just taking the bar of that. And then the same thing is true for multiplication. If I'm multiplying a bar times b bar, it's the same thing. I can multiply those two, the original integers together. I don't have to find the congruence class initially, but I can do the multiplication with the original integers and then find the congruence class. So this is a really nice kind of elegant way to deal with this. It means we don't have to change everything out of a number system we're familiar with initially. We can work with it, and then, at least as far as addition and multiplication goes, we can then turn it into modules. So it's kind of a very powerful and elegant way of working with this, and the proof for this has been done. So so we've got these two pieces, but the question is the one up here, does that also work? Is that also something that is well defined? And so let's think about that. The best way I think to do that is probably to consider an example in a case. So I'm going to just kind of shrink things, move it up here a little bit. Let's start with something simple. Let's let n equal 3. So we're looking at z sub 3. We don't want to make it too complicated. Z sub 2 is a little too small, but z sub 3 is something we can work with. So let's take the example of 2 bar to the 2 bar. Okay, fairly straightforward. These are all numbers we can work with. So if we think about this, this is, if we're going to use our rule, then that means I can rewrite this as 2 squared, and I'm going to take the bar of that. So far, so good. 2 squared, as we all know, is 4, so I can write this as 4 bar. I could stop there. I mean, there's actually nothing that says I have to continue, because all this is saying is the set of the congruence class that includes the number 4 in it. So there's nothing wrong with me saying that, but let's go ahead and do the reducing and think of it in terms of the modulus. So the remainder when we divide by 3 is going to be 1. So this is the same thing as 1 bar. Okay? Straightforward, seems to work. I mean, that looks good. But let's think of a slightly different case. What if, well, what's another number in the set of 2 bar? So if I'm thinking of 2 bar in mod 3, well, isn't that the same thing as 5 bar? Same thing. They both have the same remainder when divided by 3, so therefore they're the same part of the same congruence class. So these two are equivalent. So let's go ahead and do 2 bar to the 5 bar. Technically, these should be saying the same thing because 2 bar and 5 bar are the same. So let's check and see what happens. So if we use our rule, I can rewrite this now as 2 to the 5th and take the bar of that. And then I'm going to go ahead, 2 to the 5th, we hopefully all know is 32, 32 bar. And if I divide that by 3, I can fairly quickly see goes into it 10 times, and I have a remainder of 2. That's a problem, because that is most decidedly not equivalent to 1 bar in z sub 3. So this is a good example of like talking about this notion of well-defined. Well-defined is something that it should be provable. But as we've talked about it in previous chapters as well, is proving something can take a little bit of effort. Disproving something just needs a counterexample, and we've shown one. So it turns out, no, this is not well-defined. So this is not a rule that we are going to be using, certainly not without any caveats associated with it, but as it is not well-defined. We can't just go ahead and say, oh, it works over here, so I'm going to assume it like these other things work as well. So while these two work wonderfully, our proposition at the top, not so much.